Hello. All right, this module is concerning electrical safety, and there's a lot of stuff in it. We're going to start off with this particular one. It's just a general thing. It's from an OSHA publication about electricity in general, and then we're going to that'll be this video, and then you're going to be a lot of videos in this module. They're going to be the different parts of subpart S, which is electrical. So let's get the screen shared. And up down in this corner, that's why I'm looking down there to get it going. There we are. Yeah, here somewhere. There we go. Okay. Let's go to the beginning. It's a good place to start. All right. Electricity. So this presentation is going to cover the basics of electricity. All right. How to protect against electrical hazards. And some other publication. In other words, this particular presentation is real just general stuff. We're not going to get real technical on this one. So what affects the flow of electricity? Electricity flows more easily through some materials than others. We all know that. Substances such as metals generally offer very little resistance to the flow of electric currents, and they're called conductors. A common but perhaps overlooked conductor is the surface or subsurface of the earth. Glass, plastic, porcelain, clay, pottery, dry wood, and similar substances generally slow or stop the flow of electricity. They are called insulators. Even air, normally an insulator, can become a conductor, as occurs during an arc or lightning stroke. So you got insulators and conductors, and those definitions, of course, they vary a little bit depending on a lot of things. How does water affect the flow of electricity? Pure water is a poor conductor, but small amounts of impurities in water, like salt, acids, solvents, or other materials, can turn water itself and substances that generally act as insulators into conductors or better conductors. Dry wood, for example, generally slows or stops the flow of electricity, but when saturated with water, wood turns into a conductor. The same is true of human skin. Dry skin has a fairly high resistance to electric current. When the skin is moist or wet, it acts as a conductor. This means that anyone working with electricity in a damp or wet environment needs to exercise extra caution to prevent electrical hazards. What causes shocks? Electricity travels in closed circuits, normally through a conductor, but sometimes a person's body, an efficient conductor of electricity, mistakenly becomes part of the electric circuit. This can cause an electrical shock. Shocks occur when a person's body completes the current path with both wires of an electric circuit, one wire of an energized circuit, and ground, a metal part that accidentally becomes energized, for example, to a break in its insulation, or another conductor that's carrying current. When a person receives a shock, electricity flows between parts of the body or through the body to a ground or to the earth. What effect do shocks have on the body? Electric shock can result in anything from a slight tingling sensation to immediate cardiac arrest. The severity depends upon the following: the amount of current flowing through the body, the current's path through the body, the length of time the body remains in the circuit, and the current's frequency. The table on the next slide shows the general relationship between the amount of current received and the reaction when current flows from the hand to the foot for just 1 second. So below 1 milliamperes, generally not perceptible. Now, milliampere is 1,000th of 1 amp. So 5 milliamperes is a faint tingle, and 6 to 30 milliamps, usually called, is a painful shock, loss of muscular control. Individual cannot let go, but can be thrown away from the circuit if extensor muscles are stimulated. 50 to 150 milliamps, extreme pain, respiratory arrest, severe muscular contractions, death is possible. 1,000 to 4,300 milliamps, so that's 1 amp to 4.3 amps. Rhythmic pumping action of the heart ceases. Muscular contraction and nerve damage occurs, death likely. 10,000 milliamps, which is 10 amps, cardiac arrest, severe burns, death probable. Now, based in most homes, the fuse box contains circuit breakers, not fuses anymore. I guess even not a fuse box anymore. Okay, it shows my age. They're usually 15 or some 20 amps. Amps, not milliamp, but amps. So it takes a lot to pop one of those. And if it does, there's a problem. So, but you can see here, 6 to 30 milliamps could cause painful shock, loss of muscular control. You can't let go, but you could be thrown away from the circuit if the extensor muscles in the body are stimulated. Depends which muscles are. So electricity, the basics. What kind of burns can a shock cause? Burns are the most common shock-related injury. An electrical accident can result in electrical burn, arc burn, thermal contact burn, or a combination of burns. Electrical burns are among the most serious burns and require immediate medical attention. They occur when electric current flows through tissue or bone, generating heat that causes tissue damage. Nasty stuff. Arc or flash burns result from high temperatures caused by an electric arc or explosion near the body. These burns should be treated promptly. Thermal contact burns are caused when the skin touches hot surfaces of overheated electrical conductors, conduits, or other energized equipment. Thermal burns also can be caused when clothing catches on fire, as may occur when electric arc is produced. In addition to shock and burn hazards, electricity poses other dangers. For example, arcs that result from short circuits can cause injury or start a fire. Extremely high energy arcs can damage equipment, causing fragmented metal to fly in all directions. Even low energy arcs can cause violent explosions in atmospheres that contain flammable gases, vapors, or combustible dusts. Why do people sometimes freeze when they're shocked? When a person receives an electrical shock, sometimes the electrical stimulation causes the muscles to contract. This freezing effect makes the person unable to pull free of the circuit. It is extremely dangerous because it increases the length of exposure to electricity and because the current causes blisters, which reduce the body's resistance and increases the current. The longer the exposure, the greater risk of serious injury. Longer exposures at even relatively low voltages can be just as dangerous as short exposures at high voltages. Low voltage does not imply low hazard. In addition to muscle contractions that cause freezing, electrical shocks also can cause involuntary muscle reactions. These reactions can result in a wide range of other injuries from collisions or falls, including bruises, bone fractures, and even death. What should you do if someone freezes to a live electrical contact? If a person's frozen to a live electrical contact, shut off the current immediately. That's the first thing you want to do. If that's not possible, use boards, poles, or sticks made of wood or any other non-conducting materials and safely push or pull the person away from the contact. It's important to act quickly, but remember to protect yourself as well from electrocution or shock. How can you tell if a shock is serious? A severe shock can cause considerably more damage than meets the eye. The victim may suffer internal hemorrhages and destruction of tissues, nerves, muscles that aren't readily visible. Renal damage also can occur. Renal means your kidneys. If you or a coworker receives a shock, seek emergency medical help immediately. What is the danger of static electricity? Static electricity can also cause a shock, though in a different way, and generally not as potentially severe as the type of shock previously described. Static electricity can build up on the surface of an object and, under the right conditions, can discharge to a person, causing a shock. The most familiar example of this is when a person reaches for a doorknob or other metal object on a cold, relatively dry day and receives a shock. If you're in an atmosphere like that and you're getting shocks all the time, an easy way to take care of that is instead, when you reach for a doorknob, take your keys out of your pocket and touch it. You'll see the spark there, and then you won't get shocked. However, static electricity also can cause shocks or can just discharge to an object with much more serious consequences, as when friction causes a high level of static electricity to build up at a specific spot on an object. This can happen simply through handling plastic pipes and materials or during normal operation of rubberized drive or machine belts found in many work sites. In these cases, for example, static electricity can potentially discharge when sufficient amounts of flammable or combustible substances are located nearby and cause an explosion. Grounding or other measures may be necessary to prevent this static electricity buildup and the results. What's the best way to protect yourself against electrical hazards? Most electrical accidents result from one of the following three factors: unsafe equipment or installation. It's intrinsically unsafe, or it hasn't been installed right. Unsafe environment, or unsafe work practices. And that can cause in a lot of cases, those three things cause a lot of accidents. Some ways to prevent these accidents are through the use of insulation, guarding, grounding, electrical protective devices, and safe work practices. Insulators such as glass, mica, rubber, or plastic used to coat metals and other conductors help stop or reduce the flow of electrical current. This helps prevent shock, fires, and short circuits. To be effective, the insulation must be suitable for the voltage used and conditions such as temperature and other environmental factors like moisture, oil, gasoline, corrosive fumes, or other substances that could cause the insulator to fail. How do you identify different types of insulation? Insulation on conductors is often color-coded. Insulated equipment grounding conductors are usually either solid green or green with yellow stripes. Insulation covering grounded conductors is generally white or gray. And ungrounded conductors or hot wires often are black or red, although they may be any color other than green, white, or gray. Before connecting electrical equipment to a power source, it's a good idea to check the insulation for any exposed wires for possible defects. Insulation covering flexible cords, such as extension cords, is particularly vulnerable to damage. So what kind of control of insulation? Insulation? Engineering control. The insulation that covers conductors in non-construction applications is regulated by subpart S 29 CFR 1910-302 through 308, wiring design and protection. Subpart S generally requires insulation on circuit conductors. It also specifies that the insulation used should be suitable for the voltage and conditions. Conductors used in construction applications are regulated by subpart K of 29 CFR 1926-402 through 408. What is guarding and what protection does it offer? Guarding involves locating or enclosing electric equipment to make sure people don't accidentally come into contact with its live parts. Effective guarding requires equipment with exposed parts operating at 50 volts or more to be placed where it is accessible only to authorized people qualified to work with it. Recommended locations are a room, vault, or similar enclosure, a balcony, gallery, or elevated platform, or a site elevated 8 feet or more above the floor. Sturdy permanent screens could also serve as effective guards. Conspicuous signs must be posted at the entrances to electrical rooms and similarly guarded locations to alert people to the electrical hazard and forbid entry to unauthorized people. Signs may contain the word danger, warning, or caution, and beneath that, appropriate, concise wording that alerts people to the hazard or gives it instructions such as danger, high voltage, keep out. What is grounding and what protection does it offer? Grounding is a tool or electrical system. Grounding a tool or electrical system means intentionally creating a low resistance path that connects to the earth. That's what's called grounding. In Europe or in England, they call it earthing. Same thing. This prevents the buildup of voltages that could cause an electrical accident. Grounding is normally a secondary protective measure to protect against electric shock. It does not guarantee that you won't get a shock or be injured or killed by an electric current. It will, however, substantially reduce the risk, especially when used in combination with other safety measures discussed in this booklet. 29 CFR 1910-304 subpart S, wiring design and protection requires at times a service or system ground and an equipment ground in non-construction applications. A service or system ground is designed primarily to protect machines, tools, and insulation against damage. One wire called the neutral or grounded conductor is grounded. In an ordinary low voltage circuit, the white or gray wire is grounded at the generator or transformer and at the building service entrance. The equipment ground helps protect the equipment operator. It furnishes a second path for the current to pass through from the tool or machine to the ground. This additional ground safeguards the operator if a malfunction causes the tool's metal frame to become energized. The resulting flow of current may activate the circuit protection devices. What are circuit protection devices and how do they work? Circuit protection devices limit or stop the flow of current automatically in the event of a ground fault, overload, or short circuit in the wiring system. Well-known examples of these devices are fuses, circuit breakers, ground fault circuit interrupters, and arc fault circuit interrupters. Fuses and circuit breakers open or break the circuit automatically when too much current flows through them. When that happens, fuses melt and circuit breakers trip the circuit open. Fuses and circuit breakers are designed to protect conductors and equipment. They prevent wires and other components from overheating and open the circuit when there is a risk of a ground fault. Ground fault circuit interrupters, GFCIs, are used in wet locations, construction sites, and other high-risk areas. These devices interrupt the flow of electricity within as little as 1/40th of a second to prevent electrocution. GFCIs compare the amount of current going into electric equipment with the amount of current returning from it along the circuit conductors. If the difference exceeds 5 milliamperes, the device automatically shuts off the electric power. The guy that built these or invented these things, I'm going back a ways, he used to show it off by, he had his daughter sitting in a bathtub in a bikini. of course, full of water, and he'd throw a plugged-in radio in the bathtub to show his PFC that they worked, and obviously they worked. Arc fault devices provide protection from the effects of arc faults by recognizing unique characteristics unique to arcing and by functioning to de-energize the circuit when an arc fault is detected. What work practices help protect you against electrical hazards? Electrical accidents are largely preventable through safe work practices. Examples of these practices include the following: de-energizing electric equipment before inspection or repair, keeping electric tools properly maintained, exercising caution when working near energized lines, and using appropriate protective equipment. Electrical safety-related work practices requirements for general industry are detailed in Subpart S of 1910 in sections 1910.331 to 335. We're going to look at every one of those too. For construction applications, electrical safety-related work practices requirements are detailed in Subpart K, 1926, 416, 417. How can you protect yourself against metal parts that become energized? A break in an electric tools or machine's insulation can cause its metal parts to become hot or energized, meaning that they conduct electricity. Touching these energized parts can result in electric shock, burn, electrocution. The best way to protect yourself when using electrical tools or machines is to establish a low resistance path from the device's metallic case to the ground. This requires an equipment grounding conductor, a low resistance wire that directs unwanted current directly to the ground. A properly installed grounding conductor has low resistance to ground and greatly reduces the amount of current that passes through your body. Cord and plug equipment with a 3-prong plug is a common example of equipment incorporating this ground conductor. Another form of protection is to use listed or labeled portable tools and appliances protected by an approved system of double insulation or its equivalent. Where such a system is employed, it must be marked distinctively to indicate that the tool or appliance uses an approved double insulation system. And we all know how do you look for that. The double insulated tool on the nameplate will have a square within a square. Well, that's double insulated. If you go to Home Depot or Lowe's and look where they have all their power tools, you'll see some that have only a 2-prong plug. And you look at the nameplate on it, and it'll have that square within a square to show it's double insulated. Proper lockout tagout procedures protect you from the dangers of the accidental or unexpected startup of electrical equipment and are required for general industry by OSHA standard 1910.333 selection and use of work practices, which we also got to cover. Requirements for construction applications are in 29 CFR 1926, 417, locking and tagging of circuits. These procedures ensure that electrical equipment is de-energized before it is repaired or inspected and protects you against electrocution or shock. And the standard, this lockout tagout standard in 333 is not much different from the one in 1910.147 lockout, which we've covered before. How can you prevent an accidental or unexpected equipment startup? The first step before beginning any inspection or repair job is to turn the current off at the switch box and padlock the switch in the off position. This applies even on so-called low voltage circuits. Securely tagging the switch or controls of the machine or equipment being locked out of service clarifies to everyone in the area which equipment or circuits are being inspected or repaired. Only qualified electricians who have been trained in safe lockout procedures should maintain electrical equipment. No two of the locks used should match, and each key should fit just one lock. In addition, one individual lock and key should be issued to each maintenance worker authorized to lock out and tag the equipment. All employees who repair a given piece of equipment should lock out its switch with an individual lock. Only authorized workers should be permitted to remove it. No two of the locks used should match. No, that doesn't matter. In fact, they want all to be the same in size, shape, or color. So you're going to get locks that match. I don't know what said that. Before working under or near overhead power lines, ensure that you maintain a safe distance to the lines, and for very high voltage lines, ground any equipment such as cranes that can become energized. If working on power lines, ensure that the lines have been de-energized and grounded by the owner or operator of the lines. Other protective measures like guarding or insulating the lines help prevent accidental contact. Employees unqualified to work with electricity as well as mechanical equipment should remain at least 10 feet away from overhead power lines. If the voltage is more than 50,000 volts, the clearance increases by 4 inches for each additional 10,000 volts. So the higher the voltage, the further away you should stay. When mechanical equipment is operated near overhead lines, employees standing on the ground should avoid contact with the equipment unless it is located outside the danger zone. When factoring the safe standoff distance, be sure to consider the equipment's maximum reach. And I tell you a little story happened when they were building a freeway in California. I guess it was lunchtime, and there's overhead power lines and all kind of equipment there. And there was 3 guys that were, I don't know what their job was, but there was lunchtime, and they were just eating lunch. They were standing, and there was a chain link fence, and they were just standing leaning up against this chain link fence, eating lunch, when not too far away, some type of equipment that was pretty high hit that overhead power line, and it was touching that fence, and it killed all 3 of them. These poor guys were just eating lunch, and they got killed because somebody wasn't paying attention to the overhead power line. What protection does personal equipment offer? Employees who work directly with electricity should use the personal protective equipment required for the jobs they perform. This equipment may include rubber insulating gloves, hoods, sleeves, matting, blankets, line hose, and industrial protective helmets designed to reduce electric shock hazard. All help reduce the risk of electrical accidents. We all know these things as PPE, and they're the last on the hierarchy of controls. Last thing we use. What role do tools play? Appropriately and properly maintained tools help protect workers against electrical hazards. It's important to maintain tools regularly because it prevents them from deteriorating and becoming dangerous. Check each tool before using it. If you find a defect, immediately remove it from service and tag it so no one will use it until it has been repaired or replaced. When using a tool to handle energized conductors, check to make sure it is designed and constructed to withstand the voltages and stresses to which it has been exposed, to which it will be exposed. What special training do employees need? All employees should be trained to be thoroughly familiar with the safety procedures for their particular jobs. Moreover, good judgment and common sense are integral to preventing electrical accidents. Yeah, good judgment and common sense can prevent a lot of accidents, as you'll probably find out in your career. When working on electrical equipment, for example, some basic procedures to follow are to de-energize the equipment. Makes sense. Use lockout and tagout procedures to ensure that the equipment remains de-energized. Use insulating protective equipment and maintain a safe distance from energized parts. What's the value of a safety and health program in controlling electrical hazards? Every good safety and health program provides measures to control electrical hazards. The measures suggested herein should be helpful in establishing such a program. The responsibility for this program should be delegated to someone with complete knowledge of electricity, electrical work practices, and the appropriate OSHA standards for installation and performance. What's the value of a safety and health program in controlling electrical hazards? Again, everyone has a right to work in a safe environment. Safety and health add value to any business and workplace. Through cooperative efforts, employers and employees can learn to identify and eliminate or control electrical hazards. So that's it for this overview here on electricity. And we're going to cover all this whole bunch of stuff in 1910.300s. And they'll get quite involved in some of the details of electrical safety. And but that's all for this one. Be safe.